Okay, so welcome to today's lecture in natural language, in neural networks and deep learning. What we today want to look into a bit is something I mentioned sometimes already. One big advantage of neural networks that they learn in between some type of hidden representations, and we'll focus today on how we can maybe use it more actively, maybe how we can steer this. And we'll see it's also like a different way of like training models. In addition to say, oh, you need to predict it this way, it will enable us to do additional control, especially helpful if we think about things we had before, like transfer learning and so on. And to do that, we'll start with the motivation of why we're interested, and then focus mainly on three different use cases where this is interesting. The one interesting thing is representation alignment, where the idea is that we're, in addition to our prediction that we're doing something, we're also like trying to ensure that in between the representation has some additional property, typically that some things are mapped together. And in some way of like improving our ability to transfer between different tasks. This can not only be interested in training, as we're doing in the first part, but also during evaluation. And that's what is referred to as classification guidance. And we'll look at that. And finally, we'll shortly have a look at metric learning, where we also use these hidden representations, but more for doing, for example, search or so, and where we try to learn good representations. But yeah, let's start with why we're interested in that. So if you remember, we had this picture quite a lot of times. This is how a typical neural network looks like. We have our hidden state, and then we have the different layers which learn different representations of the input. And in the end, we'll have in green there our output layer. And in training, we're comparing this one with our output layer. And how we're training the models, you should know, hopefully, that it's like we're comparing our prediction with some reference, and then we are learning our weights here in a way that it will predict something very similar and something very good. And so all the feedback we're getting up there, and in between we're learning some different representations, different hidden states, different ways of viewing at our input, so that the hope is, of course, the more up we go, the better we have a representation that it's easy to do our tasks. And these hidden representations in between are, of course, a bit of byproduct, something that is just there because of the network. But we have already seen that this is something really interesting. So if we think about, if you remember in transfer learning, we showed that, yeah, sometimes it's good to learn something in between, and you can reuse that for another task. So what you can do is take these representations of the input you use and use that then for another task and also solve these tasks. But the question is, can we have some type of other application, additional applications, where it is useful to have a look at this or to control them? And that's what we want to look into today, is that we'll directly investigate or change our hidden representations in addition to our standard signal we get, or as a replacement for our standard signal. Where can that be? And one case we have seen already, and that is the idea of transfer learning. But we'll do it today in a bit of a different way. So in transfer learning, we have seen that these representations are helpful. You can train your network on next word prediction. We have that seen in self-supervised learning. Then you replace some type of the network with a different one, and then you'll learn it to do a machine translation or to do anything else. So you have learned then here in between, what you've learned is a representation of your input, which is not helpful only for your original task, but it is also helpful for the other task. However, what we have done is, in our first step, in our training, we haven't put any focus that we are directly learning a representation which is helpful. We're just using only our task. So in order to learn the representation, we only get our feedback signal from the chart. However, it might be in some situation that we have as a human, some intuition what should be important or what could be encoded in the hidden representation. To think about it, what do you think could be something that a human is assuming, which could be helpful if you think about, for example, maybe first in language, if you see about multilinguality. So you want to have input in different languages. Could you imagine that there is some property which might be interesting to encode here, which is helpful for like being able to process many languages? Yes?
Avoid redundancy by connecting similar words of different languages.
Yes. So connect similar words of another phrases. Another way of phrasing that is, if you're interested in like transferring between languages, it would be nice if the representation of the English input and the German input are somehow similar, because then it doesn't matter what input you put in here, you can always like from there on process the same way. That's like a transfer. So you learn something in English, and if you then want to do the same task in German, of course it would be nice if the representation of German and English are the same, because then it's very similar to do this task. If you do machine translation, if you want to translate from English to French, and then you want to have the same model do German to French, of course it would be nice if the representation are the same, because then you only have to learn how to generate from this one into German. And in our current learning, when we're doing it, we never try to enforce it. The only thing is, what we did is we're like trying to do the prediction. So in multilinguality, like one aim would be, or one nice thing is, the idea is you have different input languages, and then you're learning into representations, and you're forcing these representations now to be similar for different languages. If they should be the same or similar, there's a lot of work on that. Of course, there's also always the question, rarely two sentences are completely the same in two languages. There might be a bit of different phrasing of it. But in general, if it's easier or if there's a more similar representation, you can do more easy tasks. If you know how to, if you want to do summarization, it might also be good that you have a similar representation, because then you can just apply the same type of summarization independent of whether your input was German or English. Of course, when we're now talking about making or like directly changing our representation, it is important what is our task. If our task is to do language ID, so you want to identify which language it is, might not be the best idea to remove the language information. But for a lot of other scenarios, that can be very, very helpful. Another example is what is referred to as multimodal foundation models. Here is such an idea of a multimodal foundation model. So we have talked a bit about like language models where you put in text and you generate text. Nowadays, with multimodal foundation models, we'll come to that more in detail, but you have a similar idea instead, that you're not only putting text in there, but you can put some system prompts, some text at the beginning. Then you put in your audio, and then you put in more text, and then you generate based on that some answer. And so what we're having now, why is it called multimodal, is that we are not only putting text into here, but we can also put audio into here, or an image, or anything else. So the idea is, in your decoder network, you have the sequence generation network, you can not only put text now in, but maybe you also want to put images or audio. And now it's again the problem. Of course, you want, I mean, typically there's much more data in text than there's multimodal data. It's always easy to get pure text data, but if you want to have different modalities, things get difficult. So again, the idea would be, if your language model is trained very good on a lot of text, how can we easily adapt this knowledge that it can also process audio as input? Now I gave you, I guess, already a good hint. So why would you assume that you want to make here similar? Yes?
Make a textual description of the audio.
Exactly. So typically, I mean, that's now the question, what is your audio? In a lot of use cases, audio is speech. So that would be like you want to make your audio, your speech and the text the same. So again, the idea is, when you put in audio into the LLM, or you can put your text into the LLM. And in order to make the learning and the transfer very fast, what would be nice is, can we like somehow learn as an additional signal? We don't want to learn everything new, but how we project our speech into the text. We just want, as not that the output is the same as the only thing, but also these representation of the audio and the same representation of the text that was said should be as similar as possible. If we force things to be similar, then we are more easily to be able to transfer these things to other parts. So it's again this idea that, yeah, if we're trying to want to project things from one from the other, it might be a lot easier if we can do that. So in the application of transfer learning, the motivation is what we want to look into. If we're doing transfer, we see that we're using now different types of hidden representation. And of course, transfer is easier if things are similar. So it might be good that we're not only training the model to do good prediction, but we're also training the model that some things should be as similar as possible, because then the type of transfer is a lot easier and can be done easier. The other use case is more the metric learning use case. And there, the idea is more, yeah, in metric learning means you want to learn a distance between two objects. So you want to learn a distance, and a distance in a way that similar examples are similar and dissimilar examples are far away. So one example is this. So for example, you want to represent images, and maybe again multimodal images and words, and then all dogs should be clustered somewhere there, and all cars should be there, and all horses should be there, or something like that. So you want to learn something that if you give in two images, and that's now more general. It's not about, we don't have neural networks here at all. In metric learning, first the idea is you can learn a metric which tells you how similar two images is, so that the distance between two cars is very small, but the distance between a car and the dog is far. And here again, this is very nicely done by a neural network approach. And this time we're doing a bit the trick. We're not really learning a metric. We are taking a fixed metric, but what we are learning is the input to the metric. And there we can again use our neural network. So now we are learning hidden representations on top of here as we had before. And that's the deep metric learning. So the idea is to learn some representation here. And the representation should be in a way that if we're calculating a distance on that, and that can be, for example, Euclidean distance, so just you take a L2 norm or anything like that, that then these two dog images are similar and to images of which are very different and different. So we are keeping, if we want to learn a metric or learn a similarity measure, we're not learning a specific measure. We're using a fixed measure, but the representation which we put in, so how we put an image into there, that's what we're learning, in the hope that we are learning a good representation. We're not looking directly on the pixels, because two dogs can be, the pixels of the image can be very different. But if we first do a lot of processing, where this hidden representation somehow represents that this is a dog and what color of the dog and so on, then this metric should work a lot better. And there's, of course, a lot of different applications for that. So the one typical is retrieval. Both, you can have it more like image retrieval. You want to find the most similar image. Of course, also for text retrieval. I don't know if you've listened to one. I mean, typically that was done by text for TF-IDF or things like that. So you look at words. You can do the same thing. You encode your question and your possible documents with a neural network into a hidden representation, and then you're learning, then you represent them in a way that important documents are like matched to the query. So in general, if you want to search something, that's of course a nice way. If you like put them into just a vector, then you can compare and find the nearest neighbor. So what you then have to do in retrieval is do the find the nearest neighbor. And then you can find the most similar document or anything like that. And what similar means has to be learned in the network and then represented in your hidden state. That's why it's so important to learn the hidden state. Depends maybe on your use case, whether you want to have focus on the content or it should be on the style. So you want to have photos on the one and images, drawings on the other side or so. That then depends on what you're really interested in. Can also be then extended to other similar things that can be, for example, open class classification. That is here. So just imagine you want to classify images. And normally, if you classify, what you're doing is you put in your softmax layer, and then you put there class 1 is a dog, class 2 is a car, and class 4 is a horse or something like that. But that means you only can classify these 3 classes. You cannot classify what a cat is or something like that. Idea here is, you have your metric, your representation space, and for each class you're interested in, you have one or several typical vectors. Like here the one for dog, here the one for horse, and here the one for car or something like that. And then the hope is, if I want to add a new class, I don't have to retrain everything. I just learn a new example vector. And if now my new image is nearer to the new example vector than to all the others, then I will classify it as this. So you can now classify to open class problems where you're not during training have to say, these are my classes, and I only can recognize these classes, but you're just comparing to all the classes that you're interested in, and then the model will tell you this is the best match because your representation is most similar. Of course, it comes, if you're doing now training on pictures of animals and you put in pictures of, scans from your heart, won't work that well because it's a very different structure, has only learned to really get good this structure. But in general, you're not limited anymore that in your architecture, you encode, this is the number of classes, but you're a lot more open to do it as appropriate for your model. Good. So before we are looking now at the first thing, so we're going back the steps to the alignment between the representations. Any more questions of what we're planning to do today? Good. So the idea in representational alignment is that during training, we add additional information besides the correct class. So here's a very simple example. So you have 2 words, 4 words, 2 in German, 2 in English. And this might be now, you just imagine you have a hidden representation mapping these words into a space. And of course, this is now 2D space because visualization gets complicated. In reality, we have 500 dimensions or things like that. And normally you learn them and the model will somehow optimize them to put them somewhere in the space so that your task is performing very well. And in general, that's a good idea. You're really optimizing it to be very good at this task. The problem is, if you're not only interested in good performance on the training data and similar data, but you also want to do transfer learning, it should be somewhere else good. So for example, if you mainly train on English but it should also be good on German, then you cannot represent that it should be also good on German within your data. Then you have to add something else in there. And so the idea is maybe we can add constraints to the model so that it's easier to transfer to other things which it hasn't seen in training. So you give it some additional rules. And the implications can then be multilingual to multimodal, but also other things. So in multilinguality, for example, for a lot of tasks, it can be the language is not really important. So don't encode the language information, remove the language information. And that we'll see there's different ways of doing that. We can either try to remove these information, or we can just have more the focus on making same things the same. So having the same word in English and German be the same. But this idea of restriction, do you remember any similar method where we also already tried to do restrictions on the model to make the model better generalized? Yes?
Regularization.
Exactly. So that is a very similar type of approach where we'll see we're doing it a bit more targeted. So for the ones who don't remember, it's quite some time ago. So the idea was we want to have a big model, but the bigger model needs a lot of weights, and somehow we want to optimize that and find the smallest model which we're going. And we found there already a nice way of doing that, we can add a term to that. So what we did is we have trained our network with our normal loss function, and then we add what is doing the regularization term, which like says, yeah, but if you have two models which perform similar, then it's maybe better to select the one which has fewer parameters or where the parameter values are lower, so that you prefer some type of model. So we are putting some restriction on the type of model we want to have by saying we prefer weights which have a small value. We already saw there that there's one challenge with this approach. Do you remember? It's not written on the slide, but generally, if we're having more things to optimize, that's a challenge. We have an additional hyperparameter here under. So if you have more several things to adapt to, you have to tell the model how to focus. I mean, should it more look on this loss, or should it more look on this loss? So that is, of course. So what is the difference? So we want to be more specific in what we're doing now. We just don't want the model to be just small. That's a good hint. But we have more information. For example, multilinguality. We want the model that should remove the language information. Or if you think about the multimodal case, we're saying whether it's audio or text, doesn't matter. It should be just the text. So of course, somewhat dangerous. There's more information in audio, and maybe you also don't want to remove all information. If you think about audio, also the loudspeaker, who's speaking, all this is encoded in the audio signal. And if you make these two the same, you of course maybe forcing the model to lose this information. Or maybe it's then easier to process further. So you have to be careful, but I mean, in general, the idea is, yeah, we're restricting our model by giving it this additional teaching signal that it should not be only good on the task, but it should have additional constraints. And the first idea is that we are removing specific attributes of the representation. That can be language we had before. Other use cases can be, for example, the gender. So if you know that gender is not important for you, or that you can easily be good on both types of genders, you can also remove gender. So there's a lot of application on what information you want to remove in order to make the representation better and be more transferred. And the idea is now what we're doing is we're making the representation the same for things which only are different in this one attribute. So if it's language, if the sentence is the same meaning in German and English, the representation should also be the same. So first, have a look at how we can do the similarity-based alignment. So the similarity-based alignment. So the idea is now, if we're looking again at our hidden space, so what we have done is we have put our input into the hidden state, and this is now 2D visualization of the hidden space. The idea is that when we're training, we're not only training that these points are somewhere and based on the loss, but we have an additional signal telling us, oh, lebe and live should be as near together each other, and arbeite and work should also be as similar to each other as possible. Because then, if they're very near to each other, it might not matter that much, and we can more easily train them to do that. So the question is, how can we do that? So how can we make things more similar? And that is luckily quite easy in neural networks, given one restriction, that we have the right data. So if we want to do this similarity-based alignment, what we need is paired data. So we need data where these two things only differ in the one attribute that we want to remove. So for example, that can be translations. You have an English sentence and a German sentence. Like here, I live in Karlsruhe und ich lebe in Karlsruhe. You put them in the same and they should be meaning the same thing. So what we now want to have is that these representations are the same. So we can tell the model as an additional signal, oh, we also want these two are somehow the same way and encoded the same way. Another example we have seen is audio with transcript, for example. And then there's different ways of what we then have to do is, like, we're generating our hidden representations, and if we have the hidden representations, we can compare them and have different losses. Typically, we can either do a similarity loss or contrastive loss, and what exactly is, we'll have a look. But the idea is, yeah, we always do what we showed before, that we are moving things next to each other. So this is a bit of a different example than before. Here, our input are single words. For the other one, the input is more a sentence. That, of course, depends on what you're doing and what type of representation you move to next to each other. Is it a representation of a word, or is it a representation of a sentence? Also, depending, of course, on what data you have. You might have like sentences which are translations of each other, but you might not have words which are translations of each other. So it really depends on what you can move together. And the main challenge is like finding the right data so that we can do that. So I hope you have like the main idea. So what you have to do is both examples you put through the same network, because normally you want to have them processed the same, and then you're learning to make these representations the same. That is a basic idea. And then, of course, we have to look now at more specific challenges. But this idea is like for all the similarity-based methods the same. We are not only training the hidden representation indirectly to do a good prediction at the top, but we are directly enforcing that some things should be the same. If any questions? Yes.
Let's say you have two words in languages that have a similar secondary meaning, and you enforce that these words are similar to each other based on that secondary meaning. However, their primary meanings differ quite a lot. Then you would enforce a rule on your representation space, which connects transitively a lot of points that really should be far apart.
Yes, that's why you should be careful with that. I mean, the thing is, it could be prevented if you just do it on data. Hopefully, your primary meaning is occurring more often than your secondary meaning. Then your primary meaning will put them apart and only like a bit move them in these few examples. But that's of course a challenge. Why? Because I mean, in that case, it's anyway helpful, or I mean, hopefully, higher wisdom of your hidden state will have not the same representations for both meanings, because typically the two meanings are different in the context. So once you see the full sentence, you should have a contextualized embedding, which is different for the two meanings, and then you'll turn them correctly apart. So what are the main challenges we want to look into further? The first is like, how are we defining our loss functions, so how can we train the model? And we'll look at the two I mentioned before already, similarity-based and contrastive ones. Then which metrics we're using. For the default case, that's very simple. We only shortly mentioned that. Things get a bit more challenging if you have sequential data. So if you think now about that, you're not having like one hidden state, but your German sentence has 5 words and your English sentence has 6 words. So how do you do the comparison? How do you compare 5 hidden states to 6 hidden states to make things correct? Okay, so first have a look at the loss function. The easiest thing is we say we want to make things the same. So the easiest thing is to have a similarity loss, which means the similarity loss is just we are measuring the similarity between we're putting the one input to the network, we're putting the other network to the input. We have these two, and then we're having the similarity, and the similarity should be as high as possible, or if it's distance as low as possible. And we're directly optimizing that. That is somehow the straightforward way. We're directly, I mean, this will get us something. We say the similarity should be very high, or if it's a distance, we say 1 divided by the similarity should be 0, and then we're optimizing them to be very, very similar. That sounds very nice, very straightforward. You directly measure that, you're optimizing what you want to have, so that's very good. Do you see any challenges with this. You do that. If you train your model in this way, that yeah, if you have I live in culture and I live in living culture, that this should be as similar as possible. Yes?
If you just want to have the word similar, one could just learn that all words are similar, but also uses just output standard association for each other. That's that for
Yes. So that is what is referred to as model collapse. So if you just learn to map every word exactly on the same hidden representation, you've achieved it. It doesn't, you can't find out anywhere whether it's German or English. Everything is the same because it's just zero. Problem is, you can't also achieve all the other things. So might not be the super good representation because there's just no information anymore, which of course there's also no information anymore whether they're different or not. And that's why just taking the similarity loss and only optimizing to that typically doesn't work. So we have to adjust that a bit. There's two ways of doing that. We'll first look how we can still use the similarity loss. And then the other approach is to use what is called the contrastive. If we want to stay with the similarity loss, any ideas what you want to do? Yes.
We could input different sentences and then say the loss is really or is negative or something like that.
That is right. That is what is referred to as contrastive loss then, so that you not only make similar things together, but also dissimilar things apart. That's one idea, one way, good way. Any other ideas? What could be interesting? I mean, we have another task typically. You're not wanting your network to only be good at similarity. Normally you have another task. And so what we saw already, we can do a combination. So by just saying, oh yeah, we're training the similarity, but we are also training that the model is good at its original task at predicting what type of sentence this is or anything like that. And then this zero is no longer helpful. That's no longer a good solution because if you do everything to the same, your model performance on the task will be very bad. So one idea is to have train the model jointly with the prediction task or the generation task, anything you have, and your similarity task. So by having this one as just one part of the loss function, you're preventing that. And again, remember the regularization. If you would train a model only with regularization loss, wouldn't be very helpful. We'll just learn that all the weights are zero and it's not a helpful model. But if you're having this only as a side constraint and you're like forcing it a bit to be there, then you can prevent that. The other idea is to have a bit two separate networks and train only one. So for example, if you have one encoder for German and one encoder for English, you freeze your German encoder and you give this as fixed. So you're not allowed to move the German parts apart, and you only learn that the English parts should be mapped to that, so they should be similar. Then you mainly from if you look at your structure again, you're forcing the structure for German and English to stay the same, and now learn that the other one is somehow mapping to there. But since you're not changing the German text, it cannot be all mapped to one part at the time. Good. Any questions to that? Then we had the other idea that you already mentioned, and that is the idea of contrastive loss. So in the idea, if we have our image again, we want that lebe and live is next to each other, and that arbeite and work is also next to each other, the same. But also lebe and arbeite should be different, and lebe and work should be different, and life and arbeite should be different, and life and work should be. So we're just having a loss which not only pulls things together, but also moves things which don't fit should be different. And now, of course, things get a little bit more difficult because what what should we use as a negative? I mean, for some, it's very simple. So some things are very different, and then it's not really a signal that they should stay the same. Finding near ones is not easy, and also the amount of pairs you already see at the very small example. Here we have 2 positive pairs, but 4 negative. If you think about a lot more pairs, then the number of negative pairs is exploding, so you cannot use all the negative pairs. So one question is, what is a good way to select your negative pairs? Any ideas? Yes? Sample is one good way, yes? Yes?
We could ignore the negative pairs that are within one language, so just use the pairs that contrast 2 different languages.
Yes, that's also. So you can have special knowledge. And often it's even efficiency is also, because if you think about million examples, that is also difficult. So what is one successful approach typically also is to just use the ones which are in the same batch, because there you're anyway calculating your embedding, and that's then more efficient. And then you're only comparing the ones in this. There's another advantage. That means each sample is occurring both in a positive and in a negative way. And sometimes for some other application, that's good that your each sample can be positive or negative. If one is only negative, so if you randomly sample, for example, the rare words, they might be mainly always negative because there are very few occurring. Then you learn to just put the rare words far away, and that's it. So that's what makes these things difficult. So if you just randomly sample, it might be that the rare words are very often negative examples, but few times positive examples. So the model learns to like widely distribute them around, which is again not a good learning thing. So in a lot of these things, using the same batch has the advantage also that each input occurs both in a positive case and a negative case. And therefore, it's not easy to just put everything together, and it's not easy to just put everything far apart to them. And then you can do like different types of losses. One very famous at the moment is what is called the info NCE, which means you're seeing here again the similarity. So what you're trying to optimize, you sum up over all examples in the batch, and then you're maximizing the expected e to the power of the similarity of the pairs. So for each pair, you're making things as similar as possible. And for each other token, you take each SI and compare it to each other pair and trying to make them as far away from each other. You see a bit similar to softmax and things. So you have a Euro patch, you have the aligned pairs, you can have an additional temperature, like how strong you want to move them and how equally. And then you're now enforcing these things. That it's no longer the case that you just put everything together and that's a simple solution, because then the lower case will also be very, very small. Good. Any more questions too? Good. Then the next thing is, how do we now compare? I mean, now there was a loss. So if we have a metric which tells us how similar or how distant two things is, we can calculate the loss. The other question is, how do we measure how similar two things are? If we have, I mean, what we normally have here is 2 vectors, and what we want to measure is how similar or how distant they are. So in generally, distance metric takes the 2 vectors, S and T, for example, and then we want to have an output, either a distance between the two or a similarity between the two, which is both a scalar value. And if you have the one and need the other, normally you can, for example, do 1 divided by the other, and then you should have. We'll see that the 2 most commonly cases is both one's a similarity metric and one's a distance. I guess you all have an idea of the 2 most common ones already. Any suggestions? So if you're there and have to do that, which metric would you now use? Yes. Yes. I have them a second today, but that's right. The other one is L2 norm. So it's just like the Euclidean distance, the L2 norm here. So you take the square, the difference of the squares, and then the square root of the sum of all this. So if S and T are vectors, for each dimension, you do the difference in this dimension, take the square of that, sum that all up, and then take the square root. Of course, you can have other L's. So you can L1, where instead of the square root, here take here the absolute value. But that is the other thing is the cosine similarity, which is calculated is based of the cosine value of the angel which is between the two, which can be calculated as the scalar product of both divided by the length of both. Or here then the scalar product again is the sum over all the products, and then you take the length of the one and the length of the other. And so this is both are commonly used. Depending on the use case, again, some of them are more useful than the others. And you see one is a more similarity metric, and the other one is a distance metric, but again, you can use both of them. However, we're now going again into sentences. There is a challenge to do with this. And yeah, I think I mentioned it at the beginning. In sentences, for example, we have sequences of vectors. So if we have a sequence of vector on the for the one example, and we have a sequence of vector on the other side, and these are not the same length, you cannot calculate cosine similarity or anything like that, because the length has to be exactly the same. You cannot compare the L2 distance between 3 vectors and 2 vectors. So the question is, what can we do? Do you have any suggestion? You have to build now a neural network. You want to do that. You generate the text. You get a sequence of vectors on the one side and a sequence of the vectors on the other side. So we can't do that at all? Or do you have any idea how to deal with it?
On maximum negative for sentences, you could just learn a representation for each sentence and divide the representations in your neural network, and then compile those.
So you somehow take the last instead in RNN or like a full sentence representation. That is good. There might be one challenge on that. Is now you make the two ones the same, the final hidden states. What have you achieved, or what might be? I mean, it's a very good idea. In some it might work, but I would see one problem where, depending on the use case, again, it might not be the best solution. Maybe you achieve that the last hidden states are the same, but if you're interested in the, maybe I should have said that. If you're interested in the intermediate ones, you're not enforcing anything about, so they can be very different. And so you're only enforcing the last to be the same, but it might happen that in between things are still very, very different. Especially, I mean, if you're interested in the RNN states, it's easy. But if you would like have some hidden representation, then put an RNN on top of that, and make to get a last hidden state, and then make only these the same. Then the RNN could again learn to just make everything to 0. They are the same, but in the representations are very different in between. When it goes in the right direction, you can have a simplified version of an RNN. And that is what is typically used there.
Average.
Yes, average. So sometimes it's good to think very simple. Hopefully you now come and argue all the things you said is wrong and can also happen here. That is true. The only thing is we don't have parameters. So I mean, what you can do is you take all your hidden states and you take all your hidden states. You do then the average of the hidden state of the one example. You do the hidden state of the examples of the other. And then you calculate the similarity. And of course, my argument from before, he can now tell me and say, yeah, but that doesn't say that these hidden states are all the same. It only says that the average is the same. So if these are all 0, and here it's like always 1 minus 1, 1 minus 1, 1 minus 1, they're still the same. So we haven't enforced them. The good thing is we are not learning anything here in between. So we can only like have the fixed thing there. And typically that is not happening that often. So it's not a perfect solution, There's better ones, but it's a very easy one, and easy solution is not to underestimate. It's often very good to have an easy solution because that can give you then also somehow good performance. And there is another idea. I only want to mention it shortly, not all the mass, but that is what is called the Wasserstein distance. And this distance, of course, has to be calculated. So there is not a problem. You have to do approximation again. But the idea is there that you can measure distances between sequences which have similar lengths. And the method is the following. So the idea is we have initially the mass distributed across the one sequence. So each element has somehow one ends of the input. And what we want to do now is to transport this one to the target sequence, where then the mass is equally distributed on the target sequence, which has length n. And the idea is now find an optimal way to move the mass, and thereby like the cost of moving from one element to the other is always the distance of the individual ones. And so you're trying to find an optimal way so that most mass is always to the easiest way. So if two words are the same in the two languages, you try to move all mass between them and have to distribute the other. And the minimum cost that you get is then the distance measured. So the idea is that you can then somehow align the n elements on your input to the n elements on the output, m elements on the output, and find the minimum way of transporting things. The mathematical way is shown here. So the distance is in a minimization problem where you sum over all the cross distances. So each element on the input and each element on the output. So everything is compared with each other. But of course, not all distance have to be good. So if you think about translation, what you really want to do is that mainly mass is transported between the ones which are translations of each other, and that the word I and Karlsruhe in the sentence is not the same, is not important, because the idea is most mass is transported from Karlsruhe to Karlsruhe. So that's why not all distances are up equally here, so all combination, but they have a weighting scheme. And the weighting scheme is here. So the thing is, on the one hand, if you sum according to m, that should be 1 divided by n, that says, okay, yeah, if you move the mass, it should be all, like, initially all mass should be equally distributed. At the end, it should be also equally distributed. And each weight has to be higher than 0. You cannot, like, do tricks of removing mass and putting them somewhere else in. But the main idea is exactly that you're now measuring somehow how similar these different sequences is by saying in a sequence to be similar, each entry in the one sequence has to be somehow matched to an element in the other one, and that distance we want to take. And that is the idea of this. Of course, you see here now we have, in order to calculate the distance, we have already to solve an optimization problem, which might not be super easy. If you want to really use that, it can be used in deep learning, but normally you approximate that with some type of approximation to do. Good. Any more questions? Okay. Then I have a short break for you. Not really, but you have to do something, but maybe don't. So it would be nice if you can, surely we have to also do the evaluation. Either you have the slides, you click on it, you make a picture, and we may take a break for 5 minutes or so, and then you can fill things out. I'll slowly continue, finish everything. I see that some people are done and moving forward airborne. So now we have we discussed the one method of making things, like how to aligning them is making things simple. There's another way of doing it, and that's try to explicitly remove information. And that is what we'll try to look at the next and how we can do that. So the idea is, can we remove the information that shouldn't be in there? For example, can we remove the information that this is text, this is English, and this is German? Or for audio and text data, can we remove the information that this is audio or this is? Why is that interesting? One big advantage is the data we need to do that. Before, we always needed paired data. So you need German and English data, or you need text data with the aligned audio. In this type of approach, we only need to have the input and the property. So what we only need is audio and the information that this is audio, and text and the information that this is text. But we don't need the matching thing. Of course, often it's easier to get independent data than getting the same. The same thing if you take about language. You just need to know the language, but you don't need now always that they are matching in translation. And so the idea is now we have our hidden representation, and then we want to remove information from there. So we want to remove the language information, or we want to remove the speaker information or the modality or anything. Again, I mean, there might be counterintuitive and you might make the model worse because this information might be helpful, but for specific scenarios, as we have talked about the transfer, this might be very helpful. So the question is, do you have any idea how you can remove information from an input? It's also in the first step, before we want to remove information, the first step maybe is good to check whether the information are there or how good they are there. So a step first to go there is to measure if information are there. So is there information that this is a German word or this is the English word? Is it encoded? That might be a good first step to remove them, because then you can also measure whether you're successful or not. And therefore, the first question is, can we somehow measure that? Can we find out whether, when we have only these points, whether it's clear that there is like some are German and some are English?
Just try to train a classifier on that and check whether it's always correct.
That's exactly the way to do it, and the easiest way. So what we're doing is now we take our hidden state, and on top of that, we're training a classifier which should predict this property which we want to remove. If the prediction is good, then it's in there, it's easy. If it's not really good, then it's not. So the idea is somehow we use a classifier. So you put in your I live in Karlsruhe, get your hidden state, and then on top you can train a classifier which says, is this representation a German one or an English one? And you first don't change anything here, so you keep this representation fixed, and you only train up there, and hopefully mostly a very simple one. And then if this is a very good performance, it's an easy task, then the classifier will be good. And if the is bad, then it should be bad. So we can just train. I put step 2 already. Sorry. I wanted to ask you about that, but that was too fast. So you can train the classifier that you have. The question is, how can we now remove this information? And that is also somehow working. So this, if we are back propagating from the classifier, we can now, we said we don't changing the classifier. Well, what we can do is we can back propagate from here, and we can store what do we need to have to change here to make our classification better. But now is the important thing. That's not what we want to do. We want to do the inverse thing, not too difficult. If you want to make things worse, you're not doing gradient descent, but you're doing gradient ascent. So what you make, you invert here your gradients, you invert your sign, and then forward this one here. So here you're learning methods so that here the classifier is really bad. So what you mean is you train your model here, this upper one. So there's again 2 playing against each other. This one is trained to be as good as possible as classification, but then you change your sign of your log, and down here the network is trained to make the classifier as bad as possible out there. And thereby you can then achieve that you have you somehow get that again, and you don't need to have this type of parallel data. Yes.
Where is the classifier applied? Because you could apply the different layers of network, right? You could apply directly a few layers after the embedding or only at the end. How do you make sure that works out?
Yes, so we'll have that a bit on a later slide, but that of course is your design decision, and is a bit application dependent on where do you want to remove this information. That's the same thing as we have the similarity loss. You can do the same question. Which representations do you want to have the same? The top, the bottom, or so on. So that depends a bit on your use case, but it's a very important question. So that, of course, you have to decide on when you do the transfer, what do you think from your intuition of the model, where should these information be removed? So that's an important question. We come to that, but it's really, even for both cases, very important. Was another question? Or?
You have to train them both at the same time later.
You have to at least, like, if you only train the lower one, it's easy to fool that. So, but that is typically one thing which is challenging. On the other hand, if you train together, it might be getting unstable. So that is one of the main issues here. What partly works in better if you like iteratively. So once train the classifier, then train here. But of course, it doesn't work. You once train the classifier, and then you only train the lower one, then it's easy. So you always have to either jointly train them or like iteratively. But that also makes, similar to GANs, things difficulty. Yes?
might not be a problem that the quality of the outputs of the first model just decreases, like that it collapses just
Yes, again, so yeah, I didn't mention it here, but model collapse can of course also happen here. I mean, it's very easy to fool the classifier by just having zeros only there. If there is no information, you cannot do that. So again, this only works, or either, I mean, so you can't do the freezing, so typically that's done as one part of the loss. So you cannot only do this loss, but normally you have to do both, training the main task, and this one is an additional task. Otherwise, you will have your model collapse. And even then, what you typically see is you're on your training data and very similar test data, you're restricting the model and the performance will go down. But the hope is it will get better on things which are more far and where you have to do this type of generalization. So what you normally do is you do your you do calculate your loss, so a forward pass, calculate your loss on the top. Then you back propagate through the classifier. You can update your weights on the classifier. You invert the gradient so that now it's not trying to make the classifier better, but making the classifier worse. And then you're back propagating further and trying here to fool the classifier to make things better. Yes, so that is a bit of one way, and you have to be a bit careful that things get stable. There is one thing which sometimes can happen is, of course, if you now train the model that if there is German input, it's English, and if it's English input, it's German, it's fooling the classifier, it's working perfect, but that's not really what we want to have. What we want to have is that they're very different, and we're not trying to now do that, they're just inverting things. So if you have your original probability, you want to have that the model predict this. If you do two big changes, it's just like predicting now another class. And most of the time, you do too small, it's doing still the right class. And so another way, instead of like inverting that, making that thing different, the other idea is now we're saying not, oh, it should be the probability. I mean, if you're inverting, mainly you're saying, oh, the probability here should be 0. And the other one, since it's an equal probability, here 0.5. But what we really want to do is like, we want to have this one. So that it's just like equal probability on all. So it just does now to equal probability. And if that's what we want to have, again, maybe it's better to just train that. And you can do that. There is this concept of KL divergence, which measures the difference between two probability distributions. And what you now try to achieve as a loss is that the probability distribution of your classifier. So your classifier always gives you at the end probability distribution over your output, over the possible classes. And you're saying this one should be the uniform distribution. So your aim is not to make this one as low as possible, because if it's equal, you're fine. Then it's more. So your aim is now to just have a uniform distribution over all your classes. And that can be a further extension to that. But again, what you're trying to do is like remove this information by having a classifier. The question is then like, how do you measure, or what is the aim to make the classifier really bad? Any more questions to this idea of an adversarial loss? Yes?
You said losses are typically added, so the different loss terms by some. Would it be possible to train another network on top of that to approximate the multiplicative loss, such that you have the stability as well as no high parameter tuning?
I mean, even if you have probability, it's not clear that just the normal probability, then you have just your weights are powers of that, and not so just having probability is not enough. And what you can try, of course, is that you train a network to predict them. The problem is what you really want to, I mean, why you're doing the additional loss is that you not only want to be good on the training data, but you'll be good, like more transferable to other things. And that's always very difficult to learn, especially if training one model takes very long. it's hard to learn a classifier on top of that. So it's possible, but in general, that is the main challenge, that one training takes very long. So it's difficult to like run several trainings and train something on top of the training procedure. Good. And then we're coming to a bit what was mentioned before already. That's the integration. And that is the question, where should you align things? So where should you try to make them similar or remove them? And when should you do it? So how should things interact? And so the first question, where do you want to force the similarity? And this is again very dependent on the application. So we want to look at two examples again, the multilingual and the multimodal case, but of course there's a lot more way into that. But just to get an idea of what to do, where to do. So if you think about the multimodal foundation model, what it looks like is you have your speech encoder, then you project it into something like the word embedding, and then you put it into your large language. And of course, the first thing is you're trying to make this projector and your word embeddings as similar as possible. So this one here, you put in your contrastive loss, for example, so that these two are very similar. And if these two are very similar, then the further processing should be the same. And then you can easily transfer. So although the language model is only trained on text, it can now understand also speech because the input looks very similar. So it's well motivated to do the contrastive. The problem is, of course, will not make it completely the same. So there is typically still a bit of things are different, and it's not like proven that at the end these things are the same. It's still minor differences, and networks are often sensitive to these things. So there might be others. And Parley was shown to work better, for example, if we're running the full LLM on both, and then you calculate the loss also on the individual layer. So mainly you say each layer should be exactly the same. So this layer should be the same, this layer should be the same, and so on. But of course, you're still only, for example, training the projection. So there's two different things, so how you measure things and what you're allowed to change. So you can, for example, say, oh, still I'm only changing the projection. But it shouldn't be that it's directly the same. It's not only important. It's also important that if I do further processing, that the results of the further processing is the same. Yes, so that sometimes works out. Now, of course, you see here already directly a bit of a disadvantage. That is, this is more processing. Not only do you have to do more comparison, you see here you can directly stop here. You don't really have to calculate all the LLM hidden states, while here you have to calculate all the LLM hidden states. Any questions? Good. In multilingual language model or large language models, one typically idea of doing that is the middle layer. Any idea why that could be well motivated here? So here it's different. So what we remove is the language ID. So which language it is. Why could you think? I mean, it's not only what motivates, you can also analyze if this looks better, but there is somehow a motivation behind that.
At the start, it might make sense to have language information to process the structure of the sentence. And the same is true for the output, because you have to output in some language. So really, the thing that should be independent of language shouldn't be generation information.
Yeah, so it's a bit like, yeah, so what you have is you have to understand the sentence first. And that, of course, is language dependent, as you said. So the idea is if you have a sequence to sequence stack, you get some language input and just have some language input. What you really want to have is you take the language specific, analyze it, get a representation that is language independent. And then when you generate, of course, you need to know the language again. I mean, it matters if you generate English, you have a different sentence structure than you have in a language in German. So somehow it makes sense to, on the top again, have language dependent representation. And that's why in that case for large language models, for example, it can be of an advantage to only enforce this in the middle of your layers so that you mainly, of course, you make things a bit more complicated. Normally, if the language model does just work on English, it doesn't need to learn some language independent representation. It can just do everything in English. Now you're forcing it to go from English to some representation where there's less English in there, and then add them again to generate your output. But it has the advantage that if you're not going from English to English, but from English to German, or from German to German, things are still similar and you can transfer ideas from between. Similar is if you're having, maybe you can remember, besides decoder only model, we also have the encoder decoder model, where you have first an encoder to process your input, and then based on this input, you have the decoder which generates your answer. And in this case, it's maybe even, for in the multilingual case, more intuitive on where you remove the language information. Then you somehow do a similar thing. So you remove them on top of your encoder, because you somehow say, yeah, you process your input. And then the representation, which is the content which was said on your input, that should be language independent, so that I can then generate in any language that I want. So in encoder-decoder models, you typically enforce then the similarity here on top of your encoder layer. Any more questions to this? Then the other questions we had that before is when do you train it? So how do you train? The one idea is, as we mentioned before already, that you do a joint training. So you jointly train both the prediction task and the similarity, for example. And the other way is that you're doing alternative training. So you do the one task and then you do the other task. The main advantage, you have to be, of course, careful that you don't do the model collapse, but especially if you think about the classifier, things get unstable if you do join them jointly, and then these things might happen. Good. Any more questions? Good. Then we want to look at one example where these things are done during training, doing inference, and that is called classifier guidance. So the idea is, again, we want to change our hidden states, but now we don't want to train something, but for example, we want to have an additional signal which we can use during inference. So the example where we want to have it, just imagine you translate from English to German or another language, they might have gender information. And these informations are not in the input. Or you want to have formality. You don't know whether you should generate Z or er, or do, sorry. And what you then can do is, during inference, you check what type of attribute he's currently generating. And then you're forcing the model to use a correct type of signal. So how does that work? So we have two types of models in that. We have our main model. You see there is an English translation system from English to German, where there's a big neural network which trains, and of course it can generate either the formal or the informal one. And then what we are doing is an additional thing. So we're not, that is the main motivation. We want to work on the hidden states, but not retrain these models. Then we can train a classifier on your top hidden state, which says, is this formal or is this not, or is it informal? And we have the two examples. And for example, informal, the first one is more formal, and you see the second one is more informal. And based on the hidden states, you can now, of course, train the model to be able to correctly predict it. And you can even train the classifier on each of the steps. So not only doing it at the end, but each step you generate, whether it's at this point is more formal or informal length. So this is all the training. You're not training the big model here. So this is millions of parameters. This is a very shallow type of classifier with Tula. How can we use that now? This classifier, now that is the difference, is not like used during training to steer things, but we're trying to steer things during inference. And how does that work? So in test time, we're again putting here our input sentence, and we're generating, and we're calculating our first hidden state. And on this hidden state, we can now apply our classifier, and we can check whether this is informal or formal. This is just applying again our hidden state on top of that. Now we can use this one to control and decide what should be the output. So we calculate the hidden state of the main model, we predict the attribute of the classifier. And then the next thing is we compare it to what we want to have. So do we want to have formal? If we want to have formal, we're saying, yeah, it should be very formal. If we want to have informal, we put the other one. Now we can measure mainly the loss between what was predicted and what we want to have. Just the classifier has predicted something, but we're saying, yeah, maybe that's not what we want to have. Now we know a way of training the classifier or changing inputs, and so we're calculating the loss here, and then we are back propagating this loss, this gradients, down to the model. But there's no one important thing. We're not changing the weight. The weights are fixed. You don't want to change. But if you remember, when we back propagate, we can calculate the loss with respect to the weights. We can also calculate the loss with respect to the hidden states. So what we can do is we can back propagate there and now not change the weights, but we're changing the hidden states a bit. Not completely, then we're generating, but we're changing them a bit so that we are getting into our, telling the model, oh, change this, not the content, but it should be the more formal answer. So you're doing the backpropagation and change the hidden states now in a way that they are more like we want to have them based on then the results, we can run again a forward pass and calculate now the new one, which has now been forced to be more similar to the formal one, and then generate a formal output. So by this means we're looking at the hidden representation. We're using the hidden representation again, but we're forcing the model to be the way we want and then change the hidden states in the way. Yes.
How do you decide when to do that?
Typically you do it at like each step. Before outputting, you want to do a backprop. And then it depends how many backprops you do, but typically like maybe one or two or very few are enough. But that's all the hyperparameters of how to do that. Good. Any questions? Hope that doesn't mean it's hot and you all fall asleep. And then we want to do one last step. So there was more like looking at adjusting hidden representations of models that we use for something else. At the end, we want to go like have a look at once again at the metric learning. And in this case, we are really most interested in learning a distance function. So what we're interested in is finding most similar examples or so. So the only interest you have at the end is the type of embedding that you want to have. And what we typically can look at there is that we can have what you can look at is typically two possible loss functions. How you make that contrastive loss, and we'll have later a bit of different scenario where you have where you have a similarity loss. The contrastive loss is similar to what we had before. So you have no paired data. You have a label whether it's similar or dissimilar. So the easiest thing is we now said you have to encode in your label which ones you want to compare as positive or negative. But of course, there are the same challenges in there then, like how to find negative central. That's always in contrastive learning a major issue. What is a good way that they're challenging enough, and so on. And then you're doing, as we had before, you minimize the distance between the positive pairs. So if they're positive, this is similar, then this should be the case. So you're trying to make very similar, and for the other ones, you do the distance. And you have a margin maybe that you don't want to make them more apart than that. The other thing is what is called metric learning. And in metric learning, you don't have pairs, but what you have is triplets, and that has to be shown for this type of learning sometimes to be more advantage. So what you have your anchor point XA, the one that you want to compare them. And for this one, you mainly have two other examples. You have the positive example where this is similar to, and you have the negative example where this is dissimilar to. So here is this one, here's the negative parallel. And then what you want to learn is, of course, make this one further away, the negative further away, the positive nearer, and there should be some margin between them, so the positive is more similar than the. So you're comparing the distance between the positive and the negative and trying to make them at least some type of margin. So again, I mean, you're using something different, something similar, but you're somehow a bit more efficient because for one example, you directly have a positive and a negative pair, which you try to use. And then you're learning them. And again, in this case, you're really only optimizing your similarity function because you want to, for example, use them then to do retrieval or anything like that. Just that you have, in this case, very useful type of embeddings that you can use. Good. And with this, we're at the end of today. Do you have any more questions? Good. Then thanks for coming today and see you again on Tuesday.